Hello everyone. Here I'd like to introduce the last section of chapter 9, absolute maximum shear stress. For maximum shear stress, actually in previous section we have talked about so-called in-plane maximum shear stress. In that case, actually we only focus on one plane stress condition, and the so-called in-plane means we only consider the XY plane and the rotation from 0 degree up to 360 degree. We all consider the stress state of them and find out the maximum shear stress among them. However, over here, we like to consider a more general condition. So let's see this condition first. Here's the first case. We have a very general stress state on a so-called differential element with three-dimensional system. So we have three normal stress together with three shear stresses together. Under this condition, if you try to find the so-called normal stress, or the principal stress and the maximum shear stress of them, first of all, we can follow this concept. We cut a corner of this element, just like this one. We call it tetrahedron, 四边形 or 四面体, sorry, 四面体. This kind of shape actually include the stress state of original stress state on three perpendicular or orthogonal surfaces. These three surfaces corresponding to all the stress states from original stress, okay? And this new surface actually corresponding to any arbitrary orientation of the surface. And we can use that to find the sigma and tau. Once we find a kind of a special or specific orientation, we have chance to find the so-called principal stresses. Three principal stresses, we call it triaxial stress. Okay, in this stress state, we have maximum, minimum, and intermediate stress states of them. Okay, and all of them belong to principal stress. And after we derive them based on our previous study, we know that if you find any principal stress, then rotate 45 degrees, you will find the corresponding maximum shear stress in that plane. So in this case, once we determine the stress state like this, then we can have chance to find so-called three maximum shear stress in each plane. Okay, for example, these two principal stress make generate a plane like this one, and then on this plane you will find so-called 45 degree, just like this angle. Okay, and find the maximum shear stress in that plane. Of course, if you take these two, you will have a plane along this orientation, and then 45 degree like this direction, you will find another maximum shear stress. Follow the same concept. Of course, you will have three maximum shear stress. However, the derivation process from this stress state to the so-called tetrahedron condition, and then goes to these three principal stress states condition, we need several high level or advanced mathematics skill. At this stage, it's probably quite difficult to allow you to learn this in your engineering mathematics. So in order to avoid this problem, we need to lower down our difficulty, and then we try to find another way and to search our absolute maximum shear stress. Here's the condition we can solve. This is called example 1. In this condition, actually, we select XY plane as a plane stress condition. For this state, for this element, okay, this element, actually you can rotate the orientation to certain direction and find the sigma 1 and 2 as principal stress states, and these corresponding coordinate system just match these two principal stresses. However, if you check the upper surface like this, we know there's no stress, no shear stress, no normal stress on this surface. Based on the definition of principal stress, actually this surface is also one of the principal direction in z direction like this. The reason is quite simple. Although you don't find any normal stress, which means normal stress equals to 0, but at the same time your shear stress is equal to 0 as well. So this point, this orientation also can be considered as one of the principal direction, okay? And the principal stress at this surface is 0, okay? So we have sigma 1, sigma 2, and 0 as the third one. We have 3 principal stress, 1, 2, and 3. Every 2 principal stresses can make one circle, one more circle for you. So sigma 1 and 2 generate one more circle for you, and the other 2 get another one, and sigma 1 to 0 create a third one. So you actually create 3 more circles based on 3 principal stresses. If you have 3 more circles, then each circle have its own maximum shear stress. Okay, we denote the name for xy plane, xz plane, yz plane. And compare the 3 maximum shear stress, we select the maximum one among them. We call it absolute maximum shear stress. The absolute value is actually the biggest one among 3. Okay, that's why we call it absolute maximum shear stress. For the second case, in this case, we also have 2 principal stress, but this one, sigma 1, is positive, this one is negative. So we have sigma 1 as positive one, negative one, and in z direction, we still have 1 as 0. So 1, 2, 3 in this system. Then 2 of them make 1 circle, the other 3 get 3, totally 3 circles. And of course, among these 3 more circles, the maximum shear stress among 3 is this one. We call it tau xy z xy maximum as a maximum in-plane shear stress and also absolute maximum shear stress. Okay, so that is the way we determine our absolute maximum shear stress in this system. So if you review these 2 cases, once you have 2 principal stress with same sign, positive, positive, or negative, negative, then you need to refer the condition of example 1, and your absolute maximum shear stress will be sigma 1 and 0 create absolute and get the absolute maximum shear stress. However, if you have principal stress with different sign, such as negative to positive or positive to negative, then just like example 2, your absolute maximum shear stress combined coming from sigma 1 and 2 this circle and get the good value from them. Here's one example as so-called surface of cylindrical pressure vessel subject to state of plane stress on its wall. Determine the absolute maximum shear stress at this point. So this is the stress state. Okay. For this stress, of course, because the hoop stress or tangential stress will be twice as much as a longitudinal stress. So in this case, we have 32 in one direction, 16 on the other direction, and orientation 45 within this surface would be, here is the orientation we'd like to see. Okay, here is the condition we try to see. Sigma 1 is here, 32, 16, and 0 for the other one. Once we have this condition, then we have these three circles. The biggest one would be sigma 1 together with 0. We get a big circle with a diameter of 32. The radius would be 16, so that would be our absolute maximum value. Okay, and of course, if you want to consider any other two maximum shear stress, then this one you will have 8 as the maximum shear stress, but your normal stress would be 24. This one, it would be 24. This one, 8 with the radius and 8 for its normal stress. For this one, 16 and 16. Okay. Here's another case. In this case, we have a little bit complex condition. We have compressive normal stress 20 megapascal in x direction, and shear stress would be 40. That would be positive. So once we have this condition, we will have another chance to find. We will have a chance to find the principal stress and absolute maximum shear stress in this case. So first of all, we need to find the center. The center would be negative 20 together with 0. 0 is in y direction, so the average would be minus 10. This point C would be 0 minus 10. Then try to plot the reference point A as minus 20 minus 40. Sorry, this is minus as well because it goes down in x direction, in the normal x direction. Okay, so minus 40 minus 20 would be A, and how to plot it? We go 20 here, 40 here, we got A, point A. Okay, once we have this circle, all right, then if you want to find the principal stress, and this circle give you the solution. Center is here, radius would be this big value. This part together with 40, so triangle like this, right triangle here, give you a line as a radius 41.2 megapascal, and then sigma 1 would be this value 31.2, okay, and the other minus 41.2 sigma 2, and the angle to theta would be the arctangent like this, a 76 degree, and theta would be 38. Once we have all these results as our principal stresses and the direction, then next one we can have chance to derive the other two circles based on them. Center would be 0, maximum would be 31, minimum would be minus 41.2. After we have them, we find that the maximum shear stress still be our largest circle, and the radius would be 41, so that would be our maximum shear stress 41.2. The center, the normal stress would be minus 10. The same, exactly the same as our original shear stress, maximum shear stress, and the normal stress. Okay, so note that since sigma 1 and 2 are opposite signs, opposite sign means positive together with negative. Okay, opposite sign. So that's the reason we have such kind of condition, and the result is just the same as our original shear stress, maximum shear stress and normal stress. Okay.